So yeah, the date now, the time now is 31st of January 2026. Time now is 11:53 a.m. Yes, I still got my board here, my blackboard in the ward. Funny enough, it's not mine, but it is like mine, so I'm using it. So this video is on the NSIGII. NSIGII, I'm so happy. NSIGII, end of November, S for Sarah, I for India, G for Golf, G for Golf, I for India. So basically, that's what I'm on the board now. It's basically on uh, dimensionless NSIGII, human rights, NSIGII, human rights, NSIGII, dimensionless time capsule lock. So it's basically the video is very important to understand. It's a time capsule lock. So you have a time capsule, which is basically s squared plus y squared equals r equals t squared. T squared is the time, and time is linear. It's non-linear, but you can explain time like a standard formula. It's basically a parabola. So you can have it in two ways, in two forms. You can have s squared plus y squared equals t squared, where t is the time and x point in space and time. X is point to the we can have the parabola y equals a negative boy couldn't decide whether to go to the radical party. The negative boy couldn't decide. Oh, sorry, that's wrong. The negative boy plus or minus couldn't decide whether to radical party. B squared missed out on 4ac over 2a. So this is probably the equation of y. The y is to x. So you get x squared plus y squared equals t squared. T is the time. The time. So this is really the fundamental of the system. So because they will come parabolas. So the parabola can be in two forms as well. So you get x squared plus y squared equals t squared. You're going to have or x squared minus y squared equals t squared. Notice that you get a conjugate to. So the conjugate to basically the minus t squared. So one thing to you is that this equation is very fundamental to understand for the system of a time capsule. So the dimensionless quantity operates in one dimension, and it's a quantity from that dimension. For example, you have if you're talking about the time in the time here and now, we're talking about here, physically being here, x, y, z, and now, the time here and now, nowhere else. But the quantity this place shares in this space at the time as a measure of the time. So, I was in two equations. I'm doing my calculator with me today. Have I? Hopefully I have. Tell me, this was not. If I do have my calculator, thank goodness. So, this is my calculator. So, the worker calculator. So you get this equation here, y squared minus, but you get a strip of time. So you get the kind of thing here. So this equation has a kind of point, a rock, a kind of point. You get the event happening. So it's basically you see a time lock. The time is for events. The time lock for events. Basically, observing. So basically, this system observes an event, it locks you out of that event. It's like if you open the file, if you try to open some kind of a module, try to open some kind of a module that using parallel, it locks you out of the whole process completely. because the NSIGII works on three trident pointers. So the trident pointers ensure the lock via the capsule. And the capsule is this equation. It's a parabola. So you get a parabola, which is this equation here. So you see, like, as you can see here, this is a parabola. It's like the standard curve up or curve up, s squared equation. But this is basically quadratic is get two as you get s squared plus y squared. It scales as you go as s equals a y equivalent. You get this kind of space here equals t equals minus t. So equals minus t squared. Sorry, minus t squared. So you get s squared. So the first curve is rising up. As you can see, first curve is rising up. So this first curve is rising up, rising up, rising up, and this square is basically rising up because it's s squared plus y squared it's going up. So x is one, b is two, one, x is two, b is four, and so on. So you get a parabola curve that's above the line, which is to t. It's touching at the t. It's equal to the t. Really a function of time, but the time is what you're measuring the space in. So you get this equation, and you get the area, you get the y, where the y is. So you now have the opposite one, which is the graph I'm drawing here, basically showing x squared plus y squared equals t squared, and x squared plus y squared equals minus t squared, which is the opposite side. Excuse me, you can get two pairs. So I'm going to draw some more lines, some more sections on this line. One, two, one, two, one. As you can see, you have quadrants, especially 1, 2, 3, 4, 5. You have five quadrants here. Now, let me show you. So five quadrants represent five events in time that happen. So t squared, 1, 2, 3, 4, 5, 6. You have six quadrants. So I want to make this five. Let me just roll this one. Yeah. So you have 1, 2, 3, 1, 2, 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. Now you have 5. So t squared divided by 5 and time divided by 5. You have to have divided all this by 5. See, so as we developing, so you have to, so if you divide t squared by 5, you have to divide all this by 5, and there'll be findings of events that happen in series. So this can be you, despite me shooting me a spider and shooting my webs across the table. Me just doing a Harlem shake. But they're happening in the frame rate of time. So if the time takes to happen is 1 second, if it happens in let's say 30 seconds of time, 30 seconds, 30 seconds. Let's say it was in 60 seconds. 60 seconds. Let's say it happens in 25 seconds, 90, 100. Let's say it happens in let's say it happens in 30 minutes, 30, no, I'm thinking of the time, what's the time? 30, 300 seconds. 300 seconds would be. Let's say it happens in 3 minutes. 3 minutes. 3 minutes. 3 minutes. So 3 minutes would be, no, 5 minutes. 5 minutes. So 5 minutes, I don't use the term 1. So I want to say 5. So we got 5 divided by, let's say it happens in 15 minutes. 15 minutes. So let's say it happens in 15 minutes. So t equals 15. T squared equals 15 squared. 15 squared will be 15 times 15 will be 225 225 255 time 2 time into time over 15 square seconds. So you get 1, 2, 3, 4, 5, 6. No, 1, 2, 3, you get 5 So you get 200. So you get each. So you get equation. So you get x squared, where x is the problem. So you get the curve. So so I'm gonna you get the curve. So let me use the curve. So let me use the graph is basically the time 200 minus 225. Okay. Let me just 15 minutes. So you get 15 minutes in time, and you get minus 15 minutes. So you get minus 15 minutes of minus 15 minutes, minus 15 minutes in time, 2 plus 15 minutes, and plus 15 minutes in time. So this curve governs kind of system of 5. So minus 15. So you get the table. So you get a table of let me try to write it down here. 15, 15. You get minus 15. Minus 15 divided by 5. So minus 15 divided by 5 will give you sorry, so minus 15. Okay. If we do 15 divided by 5, will give you 3. 15 divided by 5 will give you 3. So you get 3 minutes to for an event to happen. To calculate one event, because if I'm shooting my spider webs, 3 minutes is one event. So every 3 minutes, a new event occurs. Because 15 divided by 5. So you get from negative, you get negative 3 quadrants. So there are 1, 2, 3, 4, 5 quadrants of time, and minus 15. So make it equal to 6 events. 6 events total. So you get 6 events you can observe. For me, do the Harlem Shake or this sort of event. But the goal of this is to have dimensional quantity. So the quantity I'm talking about here, so if you go to the table here, so you get x squared, x. So if x is minus 1, x is minus 1, okay, x is 1, x is 1, no, x is 1. The event is the x is 1. X is 1. X is 1. Then x squared is 1. X squared, x is 1, x 2, 3, 4, 5, 5. So 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we get x is 1. X squared is 1, 2, 4, 9, 16, 25, 36, 49, 62, 64, 64, 81, 100, 121, 11 times 11, 131, 131, 144, 31 is 69, 30 times 13 is 169, 169, and 14 times 14 is what? 2016, and 15 and 15, 15 times 15 is what? 225. 14 times 14 to the power of 2. 196. So you get x and y from 1, 4, 9, 6, 16, 1, 9, 16, 25, 16, 36, 49, 64, 81, 100, 121, 144, 166, 196, and 255. But it's basically x and y at this point in time, but it's a mapping. You can have a value 25, 25, 2, 25, 25, 25, 2, which is x times x to the power x times 5, x times 5 is 25. 25 to 25 to 16. So you get 25 to 16. So 25 squared to 15 is 25 comma 16. But this basically means that x is 5, when x is 5, um, uh, uh, um, when x is 5 and y is 4, you have the area 25, 25, 25, 16. So you got 25, 16. So this is basically in a space of time. If you have 5 units, so 5 units would be again 5 quarters. So if we do 15 divided by 3 divided by 5, you divide it by 5, 1, 2, 3, 4, 5. You get 3. So you get a beginning, middle, and end. So you get 15, 15, 15 divided by 5 will give you 3. 3. So you have to split it in 3. So 3 will be 5, 1, 2, 5, 10, 15. So this represents, so 25 is in the beginning column, so beginning, middle, and end of the frame rate animation. So where does the dimensional quantity, so this is basically the category index of the system. So if you have a category index, basically a category index same system, this is what it is, looks like. So basically you can index the last data 5 to 5, which was the area of 35. But the category is A, B, C, or beginning, middle, and end. So this is like a storyline. So you can look at categories instead. So the beginning represents the beginning of the time graph. The middle of the time momentum, it can be sparse. So you can have something that maps. So it's a mapping of a category. And the categories are homogeneous only, but they're heterogeneous in time. They're homogeneous only, but they're heterogeneous in time. So when they're running, they represent homogeneous. So it's a category map in memory that's done for some. For example, if you have for the first quadrant, the first 23, you can have so for example, for me to go from 5 to 25, which is 5 4 to another category like a 4 5, 4 5, 4 5, which is basically index 4 5, index 1 2 3 4, 0 1 2 3 4, 0 1 2 3 4. So which is 416, 416, 425. I just use the map. I use the same structure, but it's a function that can transform through all these maps seamlessly. So it's not gonna have a hash table lookup. If you use it's its own hash table. It's its own hash table. It's its own hash table. So it can hash itself. It doesn't need an external input to hash itself. If you're storing data in the area, because the area can be bytes of space allocated to some system. But it's basically meant to model time dynamically. So it's a time lock. So it's a parallelism time lock. So it locks you out because of the time, not because of the space around you. So that's the time lock. It's a dimensionless quantity. So that's how that works. So how that works with time lock is basically you have a pointer to the data. Pointer. So you can have a cone which is 1 to 2 pi r 1. So you have some kind of search space you're looking for. So you're searching for your operating on this one, the middle time, which is the mapping of 636 to 1000, which is basically quadrant 2, the second quadrant of time. You can use the second quadrant of time. You use the three quadrants. You get to have one fourth. So if you use a full quadrant, that means you are using 2 pi r. So you can have one. Sorry. So if I'm going to pi now. So this quadrant here. So you get something to hold. So you get a -1 holding space. So you use two tridents, 3 pointers to do it. So 3 pointers to the data will be to the first quadrant, to the second quadrant, to the third quadrant, only needed to hold something out. So it locks you out via interdependency. So it locks you out because you are, it's also in time. It's not indefinitely. It locks you out to the operation is complete. So you cannot tamper with the process because it works in time, not space. It doesn't. It's time for it doesn't use to allocate. It's not like a byte. It looks at because there's space for the time. It's looks at because of time. If this book is born in time and it's allocated in time, not space. Via the 3 pointers. So the lock is basically cryptographically safe because you have normally use two public keys to one private key. But the public keys are timed down. They are not spaced down. They are 2 to 1 market of two public keys, which is two public keys. So that gives you a public key to distribute the entropy of the system. So if the first public key, if my public key is entropy, your public key is assuming entropy, but they're entangled in a way that the private key is intact in the system, and I own private key, or vice versa. If I have two private keys for two parts of mine, two people working on me, it wouldn't be downloading new code OS. And for my new formula, K for kilo, O for Oscar dash O for Oscar dash Sarah. You have obviously, but the time lock. So the time has to run out dimensions. So you can think of the time as this kind of pointer. So you have a common model. So you have pi r squared. So you have pi r squared. Oh, I can't find pi here. Times pi r squared times height. So you have half times base times height. Half times base times height. So if I get my calculator here, half times so you have pi r squared, which is so you have pi r squared. Pi r squared is the surface cone of the surface, and the cone represents the pointer basically. Because it's a three-dimensional system, it looks like it's a machine tape, a Turing machine. But I'm going to come back to the equation here. So the equation here is basically determining y, and y is not. Sorry. You can use this equation. You can plug in y as the intercept form because the y is the plug equation in the success as well. So if you plug in a two, sorry about the y. So in the real world, you use the y as a parabola, but my video is running out of time, so I can't really translate that. So if, for example, so in the real world, you have 4 quadrants, which is like you have to split into 4 quadrants. Doesn't matter. It's actually you have to split into four. So you have 4 quadrants of time. So it's a negative boy square. So if you have y to the y4, but x equals 4, y equals 3. So you get negative 3 squared, negative 3 minus square root of negative 3 of 3 squared. Sorry. So you get so you get 3 squared. 3. So y equals 3, x equals 4. So 3 times 3 squared. 3 times 3 is 9. Let's pick two columns. So let's pick the middle column. Y equals 6. Y equals 7. So y equals 7 will be 7. Because the y, listen, you have to have something to trace the time whilst preserving the x. So, they work on disjoint derivatives basically. So we get y equals 6. Y equals 7. 7 minus a. 7 okay. You get minus 7 minus b squared minus square root of 7 minus 7 squared times 7 or 7 squared minus 4 minus 4 minus 4 AC. So A is basically the input of XYZ. A is basically the quadratic expression. So you get the quadratic form from the quadratic expression, which is A squared plus B squared. Basically, they work in simultaneous equations too, so they are disjoint because time is disjoint from space. So you have to disjoint time first. So to get space, so you have to separate what can put in time, and that time is basically let me write it down. t squared. So you get time equals 2 into 5 t squared. So the t squared is time. So you get 15 t squared um, uh, minus 2 minus so you get ax plus by plus c equals 0. So this is quoted from ax squared. Ax squared. So ax is basically a number a, and that number is 15 minus 15. So you get I'm here minus 15 times 15 times b, which is the intercept of 15. Times 15 times 15 times 15 times 15 times c. Where c is the intercept. So c is let me give you a number of c. C is basically um, the answer. C is basically the joint. So let's say c is halfway between c is 15 divided by 2, which would be 6. So c is this. C is 15 divided by 2. This is 5. No, 15 divided by 3, which is 5. So c is times 5 times 5 equals. So you get minus 2. So basically, the term is, so I get the number minus 3. Okay, so yeah, divided by 2a, divided by 2, 2 times a, and a is 15. I get minus 2.441431944. Basically, this basically represents the negative solution to the problem on time. But there's a third solution, which is basically x y is equal to x is equal to, but the related to time. So I'm trying to distribute the time from the system. So the minus because I got put in 7, number 7. So when y equals 7, the parabola results to minus 2.441392. We get three numbers. You get a positive one, a negative one, and the x, which is the constant space of x squared. Because x squared has 2y squared, 2 ways to compute y via the time series. So the time sequence is basically half double time. If I have double time would be 30. Half the time would be 15 divided by 2, which would be 15 divided by 2 in time. So that's how I was. So this basically you can set t to half, like t to 0.5 or 0.5. This 0.5 is half the time. So t to half. You can work with small multiplication. If t equals to half, then t squared equals a quarter. So you can work backwards in time. So it allows you to work back in time to hold space and memory over a system of linear simultaneous equations. When you plug it in, so if you get t equals to half, 1 divided by 2, that means a half squared is a quarter. And that quarter in time is what you're measuring, what you're observing, that's space in time. So the goal of this time capsule, which is the graph here, is to measure any series of events that's happening to the NSIGII protocol via peer-to-peer topology. So you have peer-to-peer, which means that via consent. So if I have one person has consent, another person has consensus, less than equal to less than consensus. Consensus means a need. You can prioritize people based on the rules you need to download micro OS first. So the system downloads because of the cone shape of technology. You get a system of consensus, peer-to-peer consensus. So you have priority of consensus before consent, and then consent before permission, and those are the three axes. So if you think of them as x, y axes, let me just write this out. Here, yeah, because I'm done with it here. So if you wrote this out here, let me go back. So if you think of a permission as an axis of consent, let me do it here. You have permission, my permission to your permission, 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 uh, uh, permission, and then you get consent, and then you have to consent to see, because consent will give you a peer-to-peer model. If both parties consent to stream code or S or play games together on a peer-to-peer topology, it works like an onion system. So the consent framework is basically two parties have to have consent to play a game, while service is downloading. But that's one group of consensus over peer-to-peer topology. They share consensus. They want to play the game. They need to play the game, because it's basically how they breathe, live, and work. But the whole goal of this is to have. I'm going to do this last one here. I'm going to do so pi r square is the system here of the code. So pi r square. So you get pi times r. Pi times r. If the radius is a half, pi times 15 squared to the power of 2 to the power of 2. Yeah, that would be square root. So since pi times r, pi times pi times 15 times, okay, to get 15 times 15, 15 times 15, 225 times pi, 225 times pi, and that will be 706.858.3 or 786.854, 859. So that will be what is shared. But this part is basically a code model of the time. So the time is basically that's fall out. The part of the computer. The code is upside down. So the code basically is a fall out of time. So the time is basically like coming out, because you go like a capsule, but the capsule is like an hourglass. So it's an hourglass model of time to lock you out for that process. And that process is whatever is being whatever it's not, it locks you out because time is necessary to download the game or system, because time is a resource in the NSIGII framework. So time is really crucial. So to download a human rights operating system, so it locks you out of certain processes that the system needs, built-in processes, of course, by macOS that you can interact with while you're downloading. So you get 706.85 858 pi r squared times 15 squared, and that is pi r squared times 15 times base. Now, if that's the base, that's the base. That's a base of 360 15 base of height. But the base is half the base is so the base times height. So if I go times height times the height of a height of 30 height of to make sure it's come with half times base. The base is times times the base. Times the base will be 20 let me do 15 times 3. Base is 15 and the height is along it will be 5. So the base is times 5 times 20 times 20, which is the base, which equals to times height, half times base times height. So the half of which is 14 times height times 2 and divided by 2. So this will give you 14,000, 14 meters, 136, 137.169 So basically, this basically configurable is viable because it's basically like an hourglass. So if you rotate an hourglass, it starts to shift. Until you get it fully rotated, it starts to time. So it's basically what an axon. So the rotation is basically depending on the net degrees. So this is like the whole area. So you have to rotate it 180 degrees. So after divided by 180 degrees. So basically, after rotate this by 78.5, 78.53, 78.539, 78.5439, which is 78.53, or 78.54 to do the misplaces to have it from an axis of 15. So the axis determines the system when we start because as soon as the micro starts, it starts to try the system. So the goal of this to have the system looks like a sand time, like an hourglass time, because when you have the hourglass tilted 180 degrees, 180 degrees divided by 180, it starts to give you a radian. So you have to have that angle, a new angle, which is what we computed now to have the system have a time lockout. So the time lockout will give you which is time first axis and via triangle pointer. So the system has to rotate on axis of dimensions, and the dimensions are just one axis, and that's what the dimension quantity is. So the dimension quantity basically ensures that the x squared plus y squared is the parabola equals t squared, and the t squared has a space. So time in space. So you have time in space to perform to perform the operation whilst mitigating adverse effects in space, which is basically like buffer overflow attacks, buffer overflows, rewrite RWX overflow because the working time via lock. So it's a lock that also locks you in time, locks space out of time. So you cannot take the time to infiltrate the protocol itself. Because the protocol would not allow you to use the peer-to-peer topology, man, one, metropolitan area network, local area network, and via the topology of the distributed architecture that distributes allocation via dynamic and static systems, and ensure that it's safe because you got a decentralized model such as peer-to-peer bus or ring topology based on the current task of consensus, which is a need, not a want. Thank you for watching this video. Like, share, and subscribe.